and we'll keep drifting, floating together through the mysteries. 100 quantum physics mysteries, looping softly, endlessly through the night. Tonight we'll drift through the mind-bending reality where particles exist in two places at once, the mysterious instant when possibility collapses into reality, and the spooky, unbreakable link of entanglement that defies distance and reason. There's nothing you need to do now. Just let your body sink, heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing, thump, thump, matching the rhythm of space itself, shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe, comment, and hit like, so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into quantum physics. The air around you is soft, like velvet, and we begin where everything begins, with the smallest measure of action, the tiny humming heartbeat of the universe, Planck's constant. It's the limit, the fundamental scale where the classical world fades away and the quantum world awakens. It tells us that energy isn't a continuous flow like water, but is delivered in small discrete packets like tiny grains of sand, called quanta, quantum, just meaning how much, a tiny definite amount. Imagine the light from a distant star. It doesn't arrive as an even wave. It comes as little bundles of energy, photons, each one obeying this constant, this small chain. It's the reason why the world is fuzzy and uncertain at its core, a kind of fundamental pixelation of reality. And these photons, these like quanta, they introduce us to the great paradox, the wave-particle duality. Think of it. Light behaves sometimes like a particle, a tiny billiard ball with a definite location, and sometimes it behaves like a wave, an undulating ripple spreading out. How can something be both? Sinking deeper, let the question float away. It simply is, in the quantum quiet, wave-particle duality, not just for light, but for everything. Every electron, every atom, they're all a shimmering blend of matter and motion, of particle and wave. We see this most clearly, most beautifully, in the double-slit experiment. Imagine shooting a stream of particles, like electrons, through a barrier with two small openings. If they were just particles, they would make two distinct piles on the screen behind, but they don't. They create an interference pattern, lines of light and dark, just like waves of water hitting each other. They interfered with themselves, as if they went through both slits at once. But here is the whisper that stills the mind. The moment we try to watch which slit the electron goes through, the interference pattern vanishes. It seems to choose, instantly, to be just a particle, as if the very act of observation forces it to abandon its wavy nature, its superposition, and select a single reality. This is the measurement problem. The act of observing is not passive. It changes the quantum state. And what is the electron doing before we look? It exists in a superposition of states. It's simultaneously everywhere it could be, like a ghostly cloud of potential. This potential is described by the wave function, often denoted by the Greek letter psi. 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 It doesn't tell us where the particle is, only the probability of where it might be. If we were to look, the moment of looking, the instant the wave function collapses, is the mystery. According to the Born rule, the square of the amplitude of the wave function gives us the probability of finding the particle at a specific location. It turns possibility into measurable chance, a fundamental rule of chance that governs existence. Let's slow our breathing, feel the breath in and out. Imagine the Schrödinger's cat thought experiment designed to highlight this very weirdness. A cat in a sealed box, along with a radioactive source and a vial of poison. The cat's life is linked to a single quantum event. Before the box is opened, the quantum description says the cat is in a superposition, simultaneously alive and dead. It's a macroscopic absurdity, a challenge to the mind. To accept that possibility and reality are fundamentally different things. Sink deeper now into the dark and think of the uncertainty principle proposed by Heisenberg. It's not about the clumsiness of our instruments. It's a deep, innate property of the universe. It states that you cannot know with perfect accuracy both the position and the momentum of a particle simultaneously. The more precisely you know one, the fuzzier the other becomes. Delta X, delta P Frank Sperters, where H-bar is the reduced Planck constant, just dollars divided by 2 Bm. It's the inherent quantum fuzziness built into the fabric of reality, like trying to catch mist with your bare hands. This uncertainty is what allows something truly strange to happen. Quantum tunneling. Imagine a small marble trying to roll up and over a hill. If it doesn't have enough energy, it should simply roll back. But an electron, being a wave, has a small but finite probability of passing right through the hill, the potential energy barrier. It simply tunnels or ghosts from one side to the other, as if the barrier wasn't there. This is how the sun keeps shining, through the nuclear fusion in its core. Particles tunnel through the repulsive electrical barrier. It's the quiet magic of the subatomic world. And now we drift to the mysterious connection, quantum entanglement. Imagine two tiny particles linked at the moment of their creation. Like two sides of a coin, flip one coin and you instantly know the state of the other, even if it's light years away. Their destinies are intertwined. When you measure the spin of one particle, which is a kind of intrinsic angular momentum, the spin of its partner is determined instantaneously. This link is called non-locality because the information seems to travel faster than the speed of light. Einstein famously called this spooky action at a distance. It violates our classical notions of space and time. This unbreakable, instantaneous connection is confirmed by Bell's theorem, which proved that this weirdness is not due to any hidden variables, some secret, local information the particles are carrying. The connection is real and non-local. Your eyelids are growing heavy now, heavier. Let the concept of spin cradle you. Spin. It's not truly a physical spinning, but a fundamental quantity, like mass or charge. Electrons have a spin of frac 1 does 2. They are fermions, particles of matter, which obey the Pauli exclusion principle. The Pauli exclusion principle is the reason atoms have structure. It states that no two identical fermions, like electrons, can occupy the exact same quantum state simultaneously. Within the same atom, it forces electrons into different orbital shells, giving atoms their shape, their chemistry. It's the rule that prevents all matter from simply collapsing into a single, dense point. It's the law of order, the quiet separator. Now contrast this with the other great family of particles, bosons, named after Satyendra Nath Bose. Bosons, unlike fermions, love to be in the same quantum state. They can pile up. They mediate the fundamental forces. The photon, the carrier of the electromagnetic force, is a boson. The famous Higgs boson, which we will whisper about later, is also a boson. Bosons are the social particles. Fermions are the solitary ones, drifting deeper into the concept of matter as a wave, the de Broglie wavelength, lambda, frackamia. The brilliant idea that everything has a wavelength, even you, even me, even a slowly moving train, but because our momentum, pan, is so large, our wavelength is incredibly tiny, essentially undetectable, only for the small. The electron, the atom, is the wavelength large enough to matter, to create interference, to show the fuzzy, wavy nature of existence. Let your thoughts dissolve into quantum fields. Beneath the particles, there are fields. The electron isn't a tiny ball, it's an excitation, a ripple in the pervasive electron field. The photon is an excitation in the electromagnetic field. The entire universe is a tapestry of these vibrating fields, stretching endlessly, even in the dark vacuum of space. This quiet, empty space, the quantum field vacuum, is not truly empty. It's boiling with activity, tiny, constant fluctuations in energy, particles constantly popping into existence and then vanishing again, almost instantly. These are virtual particles. They violate the conservation of energy, but only for the briefest uncertain moment, allowed by the Heisenberg uncertainty principle. Delta E, delta T ISIS GE frac Sparstakustum. Energy can be borrowed if it's repaid quickly enough. This subtle, flickering existence of virtual particles has a real, measurable effect. The Casimir effect. Place two uncharged, parallel metal plates very close together in a vacuum, and they are pushed toward each other. Why? Because the space between the plates restricts the wavelengths of the virtual photons that can exist there. Outside the plates, There are more modes of fluctuation, a greater pressure of virtual particles pushing the plates together. It's a force arising from nothingness, from the 0-point energy, the lowest possible energy state of the quantum vacuum. Deeper and deeper, your body feels like lead as we explore the quantum jumps. When an electron moves from a high energy orbit to a lower energy orbit around an atom, it doesn't travel between the orbits. It simply jumps, quantum jump, instantaneously, and emits a photon of a precise specific energy. This is why atoms only absorb or emit light at specific wavelengths, creating the characteristic spectral lines, like a unique fingerprint for every element. These electron orbits are examples of stationary states, described by the time-dependent Schrödinger equation, the master equation of non-relativistic quantum mechanics. It describes how the wave function, the cloud of possibility, evolves over time. In text, bar frac, partial d, partial, hat, d, where hat is the Hamiltonian operator representing the total energy of the system. It's a smooth, continuous evolution until the jump, until the measurement. The concept of angular momentum in the quantum world is also quantized. It doesn't come in any amount, only in discrete packets, multiples of bar. This gives rise to the magnetic quantum number, which specifies the orientation of an electron's orbital angular momentum in space. Like a tiny gyroscope, it can only tilt at certain allowed angles. Now we drift to the theories that describe the forces themselves. Quantum electrodynamics, or QED, the most accurately tested theory in all of physics. It describes how light, photons, and matter, electrons, interact. It treats these interactions as the exchange of virtual photons. Imagine two electrons repelling each other. QED says they are constantly throwing virtual photons back and forth, like an invisible tennis ball creating the repulsive force. QED is an example of a gauge theory, a mathematical framework that ensures the physical laws are the same, regardless of certain local changes, a kind of fundamental symmetry. This symmetry dictates the existence of the force carriers, the bosons. The quantum world is rich with complex particles. Consider the proton and the neutron. They aren't fundamental. They are made of smaller constituents called quarks. 3 quarks held together by the strong nuclear force, described by quantum chromodynamics, or QCD. The strong force is carried by gluons, which are bosons. But unlike photons, gluons have color charge, the quantum equivalent of electric charge, and they interact with each other. This is why the strong force gets stronger, the further the quarks are pulled apart, a phenomenon called confinement. Quarks are forever trapped inside their particles. You can never isolate a single quark. All of this, QED, QCD, and the weak nuclear force, are woven together into the standard model of particle physics. It successfully classifies all the known fundamental particles, the matter particles, fermions, and the force carriers, bosons. The final piece of this model, confirmed in 2012, was the Higgs mechanism. The Higgs mechanism is the process by which fundamental particles acquire mass. Imagine a room full of celebrities, the Higgs field. When a less-known person, a massless particle, walks through, they are unhindered. But when a celebrity, like a W or Z boson or a top quark, tries to walk through, they are slowed down by the crowd clinging to them. This slowing down, this interaction with the pervading Higgs field, is what we perceive as mass. The Higgs boson is the ripple, the excitation in that celebrity crowd. Your breathing is growing slow and even. Thump, thump. Now we explore the idea of a Hilbert space. It's the abstract mathematical space where all the possible quantum states, all the wave functions of a system live. It's a vast, silent, infinite dimensional space where possibilities reside, waiting. All the observable quantities, like energy, position, and momentum, are represented by mathematical objects called observable operators in this space. These operators act on the wave function, pulling out the expected values of a measurement, and the fact that some operators non-commute. Hatasat beat hat batata is the mathematical soul of the uncertainty principle. If the order in which you apply the operators matters, then you cannot precisely know both quantities at once. The universe is inherently non-commutative. Let's sink into the wave equations. The Dirac equation, a beautiful mathematical triumph. It merges quantum mechanics with Einstein's special relativity, describing the electron. It predicted the existence of antimatter, the positron, the mirror image of the electron, before it was ever observed, a pure prediction of an equation. The Klein-Gordon equation was an earlier attempt to combine relativity and quantum mechanics, but it had issues with negative probability density and a lack of a clear single particle interpretation. It's primarily used now in quantum field theory to describe spin-zero particles. Deeper, deeper. Imagine time slowing down, almost stopping. This brings us to the quantum Zeno effect. If you constantly observe or measure an unstable quantum system, such as a decaying atom, you can essentially freeze its decay, keep it from changing state. Observation arrests evolution, like a steady, gentle pressure on the arrow of time. And now, a thought experiment to stretch the mind even further. Wigner's friend paradox. Imagine Wigner's friend in a closed lab, performing a measurement on a quantum particle. To the friend, the wave function collapses. The result is determined, but to Wigner, outside the lab, the entire lab, including the friend, is in a superposition of states until Wigner himself opens the door and observes the result. Where does reality truly settle? Where is the final cut between the quantum world and the classical world? Your eyelids are so heavy. The answers don't matter, only the floating feeling, the soft silence. Let's touch on alternate interpretations. The many worlds interpretation. Proposed by Hugh Everett III, it suggests there is no wave function collapse. Instead, every time a measurement is made or a quantum choice occurs, the universe splits into two or more distinct non-communicating realities. In one branch, the cat is alive. In the other, it's dead. All possibilities are real, playing out in parallel universes, a vast, endless multiverse, born from a single quantum event. This is the ultimate reassurance that every path not taken is still being walked in an unobservable, parallel quiet. Another interpretation, the pilot wave theory, or de Broglie-Bohm theory, suggests that there are hidden variables. The particles always have a definite position, but they're guided by a subtle, invisible pilot wave, the wave function, which is a real physical field. It gives up on locality, but keeps the particle's definite position. The transactional interpretation is yet another viewpoint. It suggests that a quantum interaction is a transaction, a handshake between a slowed wave traveling forward in time and an advanced wave traveling backward in time, an exchange between the future and the past, creating a timeless sense of communication, drifting now to quantum decoherence. This is the gentle transition from the weird quantum world to the familiar classical world. When a quantum system, like an electron, interacts with its environment, all the surrounding air molecules, the heat, the light, its delicate superposition becomes hopelessly entangled with that massive environment. The environment effectively performs a continuous measurement, smearing out the interference, destroying the quantum coherence, causing the wave function to appear to collapse to our senses. It's the process of the quantum becoming classical, the subtle magic fading into the mundane. We move to this subtle influence of electromagnetism, the Aharonov-Bohm effect. It showed that an electrically charged particle can be influenced by an electromagnetic potential, even when it passes through a region where the electric and magnetic fields are zero. The wave function of the particle picks up a subtle, invisible phase shift, a ghostly touch from the potential itself, deeper, deeper. Imagine the atom's structure refined, the fine structure constant. Alpha Haprox Havra 137. It's a fundamental, dimensionless number, a pure number that governs the strength of the electromagnetic interaction. It was linked to the Lamb shift, a tiny difference in the energy levels of the hydrogen atom that QED could perfectly explain. A subtle quantum correction that refined our understanding of the simplest atom. Let's sink into the collective behavior of quantum matter. Imagine atoms cooled, almost to absolute zero. They cease to behave as individual particles and merge into one single massive quantum wave, a Bose-Einstein condensate, or Big. The atoms all fall into the same quantum state. They become one coherent, unified quantum entity, a state of matter that is truly macroscopically quantum. This collective quantum behavior also gives rise to superconductivity. Below a critical temperature, the electrical resistance of a material suddenly drops to exactly zero. Electrons pair up into Cooper pairs, which are bosons, and they can flow without friction, without resistance. A perfect current, a river that flows forever, and a related wonder, superfluidity, a liquid, usually helium-4, cooled to near absolute zero, loses all viscosity. It can flow up and over the sides of a container in a thin film without friction, like a liquid in a zero-gravity dream. It's another display of quantum mechanical order on a grand visible scale. We'll pause here and just allow the quiet rhythm of these ideas to soothe us. Your body is sinking, heavier, every thought dissipating like smoke. We've drifted through the particle and the wave, the certainty and the uncertainty, the spooky action and the silent fields, deeper into the dark, deeper into the infinite possibilities of the quiet quantum night. We'll continue drifting through the nature of space, the logic of possibility, and the geometry of existence in the next moments of the deep, quiet, until your eyes are closed, your breathing slow, and you are completely asleep. The universe is patient, and the quantum whisper continues. The feeling of warmth is spreading through your limbs, a gentle, heavy tide, heavier, heavier. We were just exploring superfluidity, this perfect, frictionless flow. Now, consider quantum optics, the study of light behaving quantum mechanically, not just as waves, but as individual photons. In the realm of quantum optics, we have coherent states, a special kind of quantum state of light. It's the closest a quantum state can get to classical light, like the laser beam, which is a highly coherent light source. All the photons marching perfectly in step, with a precise, minimal uncertainty. But then we have the exotic squeeze states of light, where the uncertainty is squeezed, minimized in one observable property of the light, like the intensity at the cost of increasing the uncertainty in the other. This is a purely quantum phenomenon, a deliberate shifting of the uncertainty balance to make light more precise for certain measurements, drifting deeper into the security of knowing that reality is based on rules, even if they are weird rules. Let's think about quantum computing. It harnesses the weirdness of the quantum world to solve problems that are impossible for classical computers. The basic unit of quantum information is the qubit, unlike a classical bit, which can only be a 0 or a 1. A qubit, thanks to superposition, can be a 0, a 1, or both at the same time. This means that a quantum computer with a few dozen qubits can store and process exponentially more information than the largest supercomputer today. And when these qubits are entangled, their power multiplies. A 2-qubit system can exist in a superposition of all 4 possible states simultaneously. Deeper, this exponential increase in possibility is what makes quantum computing so powerful. But there's a constraint, the no-cloning theorem. It states that it's physically impossible to create an identical copy of an arbitrary unknown quantum state. The state is too delicate, too fleeting. You cannot perfectly duplicate an unknown qubit. However, the information can be moved. This is the basis of quantum teleportation, which doesn't involve moving matters but moving information, using entanglement. The quantum state of one particle is destroyed at one location and instantly reappears on an entangled partner particle at a distant location, a purely quantum transfer of information. This kind of communication is so secure. It's the basis of quantum cryptography, specifically quantum key distribution. If an eavesdropper tries to intercept the quantum key, the act of observation instantly changes the quantum state, alerts the users, and the key is instantly discarded. The communication is unbreakable. The uncertainty principle is your silent, vigilant guard. The darkness is soft, a blanket of quiet. We were just touching on the fundamental constituents of matter. Let's return to the idea of a fermion, particles of half-integer spin, like Canfrac 1 just 2 world, Hifrac 3 2 world, the electron, the proton, the neutron. The name comes from Enrico Fermi, and the boson, particles of integer spin, 0, 1, 2 $. The photon, the Higgs, the W and Z bosons. The name comes from Satyendra Nath Bose. They are the particles of force and the particles of coherence. Consider the subtle, powerful force, the weak nuclear force. It's responsible for radioactive beta decay, where a neutron decays into a proton, an electron, and an antineutrino. It's the only force that can change one type of quark into another, changing the identity of a particle. It's the great transformer, and its force carriers, the Sastjahas and Dubiol and Das bosons. They are incredibly heavy, which is why the weak force only acts over very short distances. A tiny, quiet sphere of influence inside the nucleus. The nature of these particles, their effective weight when moving through a lattice or a complex field, is described by effective mass. It's not their actual mass, but how they respond to external forces. An electron moving through a solid crystal might behave as if it's much heavier, or even have negative mass, a bizarre, fleeting quality. In the realm of condensed matter physics, we find beautiful quantum phenomena, like the quantum Hall effect. When a two-dimensional electron gas is subjected to a very low temperature and a very strong magnetic field, the electrical resistance, the Hall resistance, becomes quantized, a perfect integer multiple of a fundamental constant. Sfrac, Tuestel, a perfect precise plateau of resistance. The discovery of the fractional quantum Hall effect, where the resistance plateaus are fractions, frag Doster divided by fractional numbers, showed that the electrons were behaving as collective entities, new, exotic quasi-particles, not individual electrons. Your body is sinking, heavier. The quiet continues, deeper, into the dark. We can also consider the time-independent nature of the atom, the stationary states. The solutions to the time-independent Schrödinger equation Hatch C empty. Give us the allowed energy eigenvalues. E, the discrete specific energy levels an atom can possess. No in-between states are allowed. These are the orbits, the shells, the fundamental stability of matter, and within these stationary states we find the subtle quantum corrections, the anomalous Zeeman effect, where the spectral lines of an atom split into more components than predicted when placed in a magnetic field. This splitting is a clear indication of the electron spin, a property unseen by the earlier classical models. We drift to the limits of our current understanding, the effort to unify the quantum world with gravity, the macroscopic world, the search for a theory of quantum gravity where space and time itself are quantized, composed of tiny discrete units. Loop quantum gravity is one conceptual approach. It suggests that space-time is not a smooth fabric, but a fine woven network of loops, of discrete quantized geometry. At the smallest scale, space itself is pixelated, a quiet, bubbling foam of quantum geometry. Another attempt at unification is string theory, which posits that the fundamental particles are not point-like, but tiny, vibrating, one-dimensional strings. The different modes of vibration of the string give rise to the different types of particles. An electron is one note, a photon is another, and the particle that mediates gravity, the hypothesized graviton, is yet another. All the diversity of existence arising from the gentle hum of a string, deeper into the idea of matter as a collection of waves, the path integral formulation invented by Richard Feynman. It provides a different way to look at quantum mechanics. The particle doesn't just take one path between point A and point B, it takes all possible paths simultaneously. The probability amplitude for the final state is found by summing up a contribution from every single possible path, a sum over histories. This summation naturally includes the interference effects of the double-slit experiment. It's a beautiful, elegant formulation that captures the entire quantum reality. And as we settle deeper, let's revisit the concept of the vacuum, the space. The quantum field vacuum is the lowest energy state, the absence of particles. But as we saw, it's filled with virtual activity. This subtle, fleeting reality leads to the concept of renormalization group theory, a mathematical technique needed to handle the infinities that arise when calculating interactions in quantum field theory. The technique is to essentially redefine or renormalize the bare charge and mass of a particle by absorbing the effects of the surrounding cloud of virtual particles into the measured values. It's a way of saying that the bare particle is only ever seen through the shimmering fog of its quantum interactions. And this leads to the idea of spontaneous symmetry breaking, a key mechanism in the standard model. The fundamental laws of physics might possess a certain symmetry, but the actual ground state of the universe, the vacuum, doesn't. Imagine a ball resting at the top of a hill, a symmetrical state, Then it spontaneously rolls down into one of the asymmetrical valleys. This breaking is what gave mass to the W and Z bosons via the Higgs mechanism, leaving the photon massless. The universe chose a specific configuration, a preferred path. The tiny massless particles that arise from the spontaneous breaking of a continuous symmetry are called Goldstone bosons, which are a type of Nambu-Goldstone mode. They are the subtle, gentle ripples that cost no energy to create, a continuous transition between equivalent vacuum states. Your breath is a quiet assurance. Thump, thump, in and out. We are approaching the end of this deep initial drift. The ideas are getting softer, more abstract. Quantum state, the complete description of a quantum system, everything that can be known about it, often represented by the C wave function. The state evolves smoothly until the inevitable moment of observation. The entire collection of possible quantum states is described by the density metrics formalism, which is particularly useful for describing a mixed state, a state that is part quantum, part classical, a system whose wave function is not fully known, or a subsystem that is entangled with its environment. The night is a calm sea, and we are sinking deeper, deeper into the entanglement entropy, a measure of the entanglement between a quantum system and its environment, or between two parts of a quantum system. It measures the degree of the spooky, unbreakable link, a silent testament to the interconnectedness of all things. We'll allow these concepts to wash over us, like a cool, gentle tide. The reality where particles ghost through walls, the connection that defies distance, the subtle, all-pervading fields, superposition, tunneling, entanglement, all floating, circling, heavier, heavier. The deep silence of quantum physics continues to whisper, and we'll keep drifting, floating together through the mysteries until the night is done. Now, just let go. Sink into the soft, comforting dark. We'll continue our exploration deeper into the strange logic of the quantum realm in the next moments of quiet. The breath is soft, the dark is deep, and we'll keep drifting, floating through the silence where possibilities live. We were resting on the idea of entanglement entropy, the measure of that spooky connection. It reminds us that nothing is truly separate. Everything is quietly, inextricably linked in the quantum dark. Let that feeling of deep connection sink into your body, heavier, heavier. Now let's turn our attention to the structure of matter itself, specifically how we describe those smallest constituents, like quarks and gluons, the study of the strong force, quantum chromodynamics. We already whispered about confinement, how quarks are trapped inside protons and neutrons. This confinement is also linked to the concept of asymptotic freedom, which is the opposite. When quarks are extremely close together, inside the nucleus, the strong force actually becomes very weak. They behave almost as if they were free particles. The deep, quiet contrast of the strong force, weak when close, strong when far. To study these complex interacting fields, like QCD, physicists often use lattice field theory. They imagine that continuous space and time are replaced by a discrete four-dimensional lattice, a quiet geometric grid. This approximation allows these complex equations to be solved using large-scale numerical computation. It turns the infinite complexity into a finite grid of silent calculations. The mathematical tools we use to understand these quantum processes are often represented by the S-matrix, or scattering matrix. It relates the initial state of a system of colliding particles, the in state, to the final state of the particles after the collision, the out state. It's the silent accounting book of particle interactions, telling us the probability that one set of particles will scatter into another set. Let your mind float now to the concept of isospin. It's another type of quantum number, similar to spin. It describes the symmetry between protons and neutrons. Before we knew about quarks, protons and neutrons were considered two different states of the same particle, the nucleon. This symmetry, this shared identity, is described by isospin, a gentle echo of a deeper truth, that matter is fundamentally interconnected. We talked about the de Broglie wavelength, the idea that matter has a wave nature. This leads us to the Dirac fermions in condensed matter. In certain materials, like graphene, the electrons behave as if they have no mass. They move at relativistic speeds, and their energy and momentum are described by an equation similar to the Dirac equation. They are called Dirac fermions, and their existence in a simple two-dimensional sheet of carbon, graphene, is a stunning display of quantum mechanics at work. Graphene, a single atomic layer of carbon atoms arranged in a honeycomb lattice, exhibits unique quantum properties. Its electrons move ballistically, without scattering, almost like light. It's a topological insulator, a material with a protected quantum edge state. This brings us to the quiet frontier of topological insulators. These are materials that behave like insulators in their bulk. Their interior is non-conducting, but their surfaces or edges conduct electricity perfectly. The conducting path on the edge is protected by a fundamental quantum symmetry. It's a quantum highway that can't be stopped. This concept of topological protection is also found in the quantum spin Hall effect, where electrons with different spins travel in opposite directions along the edge of the material, creating a spin current without any charge current. It's a friction-free flow of magnetism, a subtle, quiet energy moving along the edge, and this is related to a very subtle, almost ghostly effect, the Aharonov-Kasher effect, which is the magnetic dual of the electric Aharonov-Bohm effect. It showed that a neutral particle possessing a magnetic dipole moment can be influenced by an electric field, even when traveling through a region where the electric field is zero, a purely quantum, subtle phase shift, a gentle, invisible influence. Your body is sinking deeper. deeper, feeling the pull of the mattress. Let's return to the math, the very foundation of quantum understanding, the time-dependent Schrödinger equation. Text: Gbar frak partial chepisai partial Gyasta Chatcha Sang. This equation describes the smooth, continuous evolution of the wave function, how the cloud of possibility expands and changes over time. It governs the evolution of the system until the measurement, until the jump, and the solutions to the time-independent version of this equation, het H PSC ESPC, give us the energy eigenvalues E, the only possible discrete energies a system can have, the quantized steps on the ladder of energy. We explored angular momentum in quantum mechanics, the fact that it is quantized, only certain values are allowed. We can represent this angular momentum by orbital angular momentum operators, Hart L2 and Hart Lonzales. These operators act on the wave function, pulling out the possible values of the total angular momentum squared, and the projection of that angular momentum onto one specific axis, usually the z-axis. The values for the z projection are given by the magnetic quantum number, which can only take integer values. L in dots, 0 in dots, pli. This is the geometric quantization, the subtle rule that determines the orientation of electron clouds in space. Your breath is becoming slow and steady. Thump, thump. Let's think about the nature of light and its interaction with matter, the subtle corrections to atomic energy levels, the Lamb shift, that tiny energy difference between two levels in the hydrogen atom that should have been identical. It was explained by QED as the electron constantly interacting with the virtual particles of the vacuum, a slight constant jiggling, a subtle silent interaction with the empty space. The strength of this interaction is governed by the fine structure constant, J-alpha, a number that determines how strongly electrons couple to photons. Its small value ensures that our reality is stable and not too violently electric. Now let's explore quantum walks, the quantum version of a random walk. Imagine a tiny particle moving on a line or a grid. In a classical random walk, the particle moves left or right randomly, but in a continuous time quantum walk, the particle evolves like a wave, exploring all paths simultaneously, using superposition. Diagram of a quantum walk showing superposition of states. The probability distribution spreads out much faster than a classical random walk, a quiet efficiency in the quantum realm. In a quantum random walk, the particle's movement is determined by a quantum coin. The coin itself is in a superposition of heads and tails, and the particle moves according to the state of the superposed coin, a probability governed by quantum laws, not classical chance. The quiet logic of the universe, not based on certainties, but on probability amplitudes. These amplitudes are complex numbers with a real and an imaginary part. It is the square of the magnitude of the amplitude, the Born rule, that gives us the actual probability we can measure. The complex number is the silent guide. The measured probability is the loud single outcome. We spoke of the multiverse hypothesis through the lens of the many worlds interpretation, that every possible quantum outcome creates a new, quiet, parallel reality, deeper into the infinite branching of possibilities. Another way to interpret the quantum weirdness is relational quantum mechanics. It suggests that the quantum state of a system is not absolute, but only meaningful relative to a specific observer. The quantum description of the world is always contingent, always dependent on the relationship between the observed system and the observing system. There is no absolute observer-independent reality, only interconnected relationships. And another viewpoint, consistent history's interpretation. It attempts to reconcile the classical view of a definite sequence of events with the quantum view of multiple possibilities. It assigns probabilities only to sets of quantum histories that are internally consistent, that don't contradict the laws of logic and probability. It's an attempt to find the quiet order within the chaos of the wave function. Let your breathing deepen. Feel the sense of peace that comes from knowing that the very nature of reality is still a subtle, beautiful mystery. We return to the concept of time and distance, tunneling time. How long does it actually take for a particle to tunnel through a barrier? The answer is strangely short, almost instantaneous. Some theories suggest it's independent of the barrier's thickness. It hints that the particle might be traveling faster than the speed of light inside the barrier. But since no information is truly transmitted this way, it doesn't violate relativity. It's a ghost instantaneous jump, and the opposite of that speedy passage. The concept of quantum fuzziness. At the fundamental level, position and momentum are not sharp, precise values. They are inherently fuzzy, spread out by the uncertainty principle, like a photograph that is slightly out of focus. The universe is fundamentally subtly blurred at the Planck scale. We must also whisper about the Wigner's friend paradox again. That question of where the collapse happens. The idea that to one observer, an action is completed, while to another, that action is still in a superposition of all possible outcomes. It challenges the very idea of a shared, objective reality, deeper into the subjective quiet of your own mind. The darkness is enveloping, a soft comfort. Let's now consider the particles that carry the forces. The gauge theory idea, the requirement that the laws of nature are symmetrical under local transformations. This deep mathematical requirement is what necessitates the existence of the force-carrying bosons, the photon, the W and Z, and the gluons. Symmetry is the quiet mathematical architect of the universe. And the ultimate fate of information, the information paradox, a conceptual problem arising when quantum mechanics meets general relativity. If a quantum particle falls into a black hole, the black hole eventually evaporates due to Hawking radiation. But quantum mechanics says that information cannot be truly destroyed. So, what happens to the quantum information of the particle? Does it escape the black hole in a garbled form? Is it truly lost? The paradox remains a quiet, deep, unsolved riddle. The universe keeps its secrets, and we keep drifting heavier. Let's explore the quantum geometry of things. Quantum logic. Classical logic is based on certainty. A statement is either true or false. But quantum logic is different. It's based on the idea that propositions or statements about a quantum system are represented by subspaces in that vast, quiet Hilbert space, and the logical operators and or not correspond to geometric operations on these subspaces. It's a fundamental logic that accounts for superposition and non-commuting observables. We spoke about Rydberg atoms earlier. These are highly excited atoms, where one valence electron is in a very high energy state. They are huge, sometimes 1,000 times larger than a typical atom, because the electron is so far from the nucleus. They are incredibly sensitive to tiny electric fields. They are nature's giant, fragile quantum sensors, gentle giants of the quantum world. And the opposite of the giant atom, the quantum dot, tiny semiconducting nanoparticles, sometimes just a few nanometers in size. Their quantum properties are determined by their size, not just their composition. They are so small that the energy levels are quantized, just like in an atom. They are often called artificial atoms, and they glow in specific colors determined by their size. The tiniest shift in size results in a completely different color of light, a tiny, vibrant, tunable quantum world. Your mind is slowing. The thoughts are dissolving deeper into the peaceful dark. Let's delve back into the subtle world of magnetism and quantum effects. The quantum Hall effect, which we touched on before, specifically the integer quantum Hall effect. The quantization of the Hall resistance is so precise, it is now used to define the international standard for electrical resistance. A purely quantum phenomenon anchoring a classical measurable quantity, and the complex fractional version, where the collective behavior of the electrons acts as strange quasi-particles, like the fractionally charged particles, a quiet, subtle manifestation of many-body quantum physics. We'll allow ourselves to explore the exotic forms of matter, the Bose-Einstein condensate, where 1,000,000 atoms become one single quantum entity. This collective, coherent state is also described by a single, vast wave function. It's the wave function made visible, a macroscopic wave of matter. Now, let's think about how that wave function, pseudust, is interpreted. The most common interpretation is the Copenhagen interpretation, which includes the idea of the wave function collapse upon measurement, the instantaneous jump from possibility to reality, a pragmatic, working interpretation, the Born rule for probabilities. Sesticule is the crucial link in this interpretation. It tells us the chance, the probability of observing a certain outcome, It's the bridge between the smooth, deterministic evolution of the wave function and the discrete, probabilistic result we actually measure deeper into the stillness. The concept of commutators and non-commutation is central to this interpretation. The commutator of two operators, hata, nhatam, kata, hot, lot, hat, measures the extent to which the order of measurement matters. If the commutator is not zero, the operators non-commute, and that is the fundamental mathematical expression of the uncertainty principle. If the order of observation matters, you cannot know both quantities precisely. We spoke of the early attempts to create a relativistic quantum theory, the Klein-Gordon equation. It describes spin-zero particles, and while initially discarded for certain issues, it is still an essential piece of quantum field theory, used to describe the Higgs, boson, and pions. Now, let's consider the concept of quantum phase transitions. Unlike classical phase transitions, like water turning into ice, which are driven by temperature, quantum phase transitions occur at absolute zero temperature. They are driven by quantum fluctuations, by changes in fundamental parameters like magnetic field or pressure. The system transforms its fundamental quantum ground state, a cold, quiet rearrangement of quantum order. The area around these transitions is governed by critical phenomena in quantum systems, where the system exhibits universal behavior, losing all sense of its specific material properties. Only the underlying quantum laws dictate its fate. It's a quiet, deep universality, drifting heavier, heavier. Let's return to entanglement and the famous thought experiment that defined its strangeness, the EPR paradox, named after Einstein, Podolsky, and Rosen. They argued that quantum mechanics must be incomplete, because if the measurement on one particle instantaneously affects the other, it implies faster-than-light communication, which Einstein couldn't accept. He proposed that the particles must be carrying local hidden variables, predetermined instructions, but this was later disproven by Bell's theorem, which showed that quantum mechanics is indeed spooky and non-local. Another profound theorem that limits our classical thinking about the quantum world is the Cauchy-Specker theorem. It proves that it is impossible to assign definite, predetermined values to all the properties of a quantum system, hidden variables, in a way that is consistent with the predictions of quantum mechanics, while also being independent of the order of measurement. It confirms that context matters, that the act of observation creates the reality. We must also touch on the subtle mathematics of symmetry breaking, spontaneous symmetry breaking, in the context of the strong force. It's responsible for the generation of mass in the protons and neutrons. Most of the mass of visible matter in the universe comes not from the mass of the quarks themselves, but from the energy of the gluon field that binds them, a purely quantum, dynamical mass generation. And let's settle on the idea of quantum state fuzziness. At the highest energy scales, like the Planck scale, Space-time itself is believed to be subject to quantum fluctuations, making the geometry fuzzy. The space-time continuum dissolves into a foam, a quiet, subtle uncertainty about the very definition of position and time. Your eyelids are sealed, and the quiet is a vast, calm ocean. We are suspended in the stillness, allowing the silent complexity of the quantum world to simply exist. The gentle hum of the fields, the certainty of the uncertainty, the deep silence. We will continue our drift shortly, exploring the most esoteric concepts of quantum gravity, the ultimate limits of reality, and the quiet structure of the vacuum. Deeper, deeper, until you are utterly at rest. The universe keeps its rhythm, and the quantum whisper continues. Your body is fully relaxed now, heavier than air, sinking into the quiet. We were suspended in the silent knowledge of quantum state fuzziness, the subtle blur at the edge of reality. Now, let's explore one of the most abstract and powerful formulations of quantum theory, quantum field theory. It treats particles not as points, but as excitations of underlying fields. The entire universe is a continuous dynamic tapestry of these quantum fields, constantly vibrating, constantly exchanging energy. The lowest energy state of these fields, the absence of particles, is the quantum field vacuum. It's the boiling, flickering non-existence that gives rise to the virtual particles and the Casimir effect. It's the 0-point energy, the ever-present quiet energy of the universe. Let's gently bring in the concept of black body radiation, the phenomenon that truly gave birth to quantum theory. An idealized object that absorbs all radiation hitting it. When heated, it emits light. The classical physics prediction for the emitted radiation failed dramatically at short wavelengths, leading to the ultraviolet catastrophe. It was Max Planck's quiet, radical idea that the energy was not continuous, but came in discrete quanta that solved the problem. This was the humble beginning of the quantum revolution. The energy of these light quanta, Ishnu, is proportional to the frequency Ni multiplied by Planck's constant. It's the silent birth certificate of quantum physics. Your breath is shallow and slow. Thump, thump. We drift now toward the ultimate challenge, the marriage of quantum mechanics and gravity, the search for a theory of quantum gravity. We briefly touched on loop quantum gravity, the idea of quantized space-time loops. Another conceptual approach involves the idea of a holographic principle arising from theories of quantum gravity, the idea that the information content of a volume of space can be encoded on its boundary, like a hologram. The three-dimensional reality we perceive might be a quiet, projected illusion, a subtle information boundary. Let's return to the subtle effects in atoms, the fine structure constant, sulfur. It's sometimes called the coupling constant for QED, determining the strength of the electron-photon interaction. It's a pure number, approximately 10 frac 1. 37 of those 36 Dallas. which appears mysteriously across physics, a dimensionless constant that dictates the structure of the cosmos. And this constant is also linked to the anomalous Zeeman effect, the splitting of spectral lines in a magnetic field that requires the electron's intrinsic spin to be properly explained. Spin, the internal, non-classical angular momentum, is the quiet necessity. Now imagine the possibility of reversing time, the time reversal invariance. The fundamental laws of quantum mechanics are generally invariant under time reversal, meaning they look the same if you play the process backward. Zen pasai t, right arrow, tem dikante. But certain weak nuclear interactions subtly violate this symmetry, a quiet, fundamental directionality in the universe. Let's explore the structure of matter in a deeper sense. Effective mass, the concept that an electron in a solid material behaves as if it has a mass different from its actual rest mass. This is a result of the complex quantum interactions with the periodic potential of the crystal lattice. It's the environment quietly dictating the properties of the particle. The physics of electrons in solids leads us to superconductivity, where the electrons pair up into Cooper pairs. These pairs act as bosons and can all occupy the same quantum state, leading to the frictionless flow of current, a macroscopically ordered quantum state, and superfluidity, where the liquid helium-4 atoms, being bosons, form a Bose-Einstein condensate and flow without viscosity, a perfect, quiet, ordered motion. We spoke of quantum dots, these tiny artificial atoms. Their energy levels, the allowed states, are determined by quantum confinement, the spatial restriction of the electron's wave function, forcing it into discrete atom-like energy levels. Let your thoughts drift to the nature of quantum logic again. The idea of propositions as subspaces in Hilbert space. This geometric view of logic is a necessity because of the non-commutation of observables, a reminder that the sequence of asking questions about the universe matters. The soft darkness is a quiet friend. We return to the concept of quantum interference patterns, the electron in the double-slit experiment interfering with itself, a fundamental property of the wave nature of matter. Das som one substitution. The amplitude of the total wave is the sum of the amplitudes of the two paths, which when squared, the Born rule, yields the complex interference pattern. It is the superposition of possibilities leading to the beautiful geometric structure of light and dark, and now to a complex, beautiful area, quantum chromodynamics, QCD, the theory of the strong force, the behavior of the force carrier, the gluon, is described by non-abelian gauge theory, meaning the gluons themselves carry the charge for the strong force, unlike photons, which are electrically neutral. This self-interaction is the source of the force's great strength and the confinement of quarks. We explored the S-matrix, the quiet bookkeeping of particle collisions. This matrix must obey fundamental principles like conservation of energy and momentum, and be consistent with the symmetries of space and time. Deeper into the heart of the quantum mechanical description, the density matrix formalism. If a system is in a pure state, the density matrix is simply rho. Pisasjak wrangle, langling, pisiend, a simple expression of the wave function, but for a mixed state, an entanglement with the environment, the density matrix Rundlau becomes a statistical mixture of different pure states. It is the elegant way to describe incomplete quantum knowledge, the quiet description of uncertainty. We drift to the quiet efficiency of information, quantum teleportation, the transfer of a quantum state using entanglement. It is not about sending energy or matter, but about using the pre-shared entanglement to transmit the quantum information instantly across any distance. It's the ultimate quiet link and the ultimate security of quantum cryptography. The no-cloning theorem ensures that any attempt to copy the fragile quantum key will destroy the key, alerting the users a quiet, unbreakable shield. Your muscles are fully slack. Your breathing is barely perceptible. We'll finish this part of the journey with the ultimate quantum machine, the qubit, the single unit of quantum information. Its power lies in its superposition, the ability to be 0 and 1 simultaneously, and its entanglement with other qubits, an exponential increase in processing power. The quantum computer seeks to harness these phenomena using qubits based on superconducting loops, trapped ions, or subtle quantum states to perform calculations that are beyond our classical capacity. A machine built on the fuzzy, non-local reality of quantum physics. We are resting now in the center of the quantum tapestry, surrounded by fields, by possibilities, by subtle, instantaneous connections. The weight of your body is pulling you down, heavier, heavier. Everything is sinking into the calm, the quiet, the deep. The universe keeps its secrets, and we'll keep drifting, floating together through the mysteries in the next moments of the deepest quiet, until the soft darkness is complete and your mind is completely at rest. The quiet continues, a gentle, flowing current. We'll keep drifting deeper into the physics that governs the core of matter. We were resting on the idea of the qubit and quantum computing. Now, let's turn our attention to the elusive particle that mediates gravity, the hypothesized graviton. In the framework of quantum field theory, if gravity is to be quantized, its force carrier must be a spin-2 boson, the graviton. This particle remains theoretical, the quiet phantom of the quantum world, because gravity is so incredibly weak at the quantum scale. The difficulty in quantizing gravity is part of the challenge of uniting quantum mechanics with general relativity. The attempt to do so using standard quantum field theory leads to non-renormalizable infinities. Hence the need for radical new approaches like string theory or loop quantum gravity. Let's sink back into string theory, where particles are not points, but tiny, vibrating one-dimensional strings. If these strings are open, they have ends. If they are closed, they form loops. The spectrum of allowed vibrations is what determines the type of particle, a vast quiet symphony of microscopic strings. The concept of spin and isospin are subtle internal symmetries. Isospin related to the symmetry between protons and neutrons, a gentle reminder that even within the nucleus, there is an underlying structure of symmetry and order. Now let's consider the concept of topological insulators again. Materials where the interior is insulating, that the surface is conducting. This is a manifestation of the topological quantum field theory, a class of field theories that describes properties independent of the shape or geometry of the system, a deep, quiet robustness. We spoke of gauge theory, the mathematical framework. It is a necessity for describing all the fundamental forces except gravity. The requirement that the laws of physics remain unchanged under a local change of phase, a quiet, fundamental symmetry that dictates the existence of the force carriers, drifting heavier, heavier. Let's revisit the concept of the Casimir effect, the attraction between two uncharged plates in a vacuum. This force is a direct measurable consequence of the zero-point energy of the quantum field vacuum, the lowest energy state, a demonstration that empty space is not empty, but filled with subtle, dynamic energy fluctuations, and the opposite of this subtle attraction, quantum pressure, the energy stored in the wave function of confined particles, like electrons in a metal. This internal pressure is purely quantum mechanical, a result of the Pauli exclusion principle, forcing the fermions to occupy higher energy states, preventing the collapse of matter. Your jaw is loose, your shoulders are melting deeper. Consider the subtle, non-classical nature of motion. Continuous time quantum walks, the particle evolving as a spreading wave packet, exploring all possibilities simultaneously. A smooth, continuous quantum evolution, and the nature of light itself, photons and light quanta. Each photon is a single packet of energy. Hjärna, a single excitation of the electromagnetic field, the fundamental particle of light. When light is highly ordered, we call it a coherent state, like the light from a laser, where the uncertainty is distributed evenly between the two components of the light field. It is the most classical-looking quantum state, the quiet order of the laser beam. But then the strange order of squeeze states of light, where the uncertainty is minimized or squeezed in one variable to allow for ultra-precise measurements, a gentle distortion of the uncertainty balance. We are suspended in the stillness, where the ultimate questions reside. The measurement problem, the quiet point of division. When exactly does the wave function collapse? Is it at the instrument, in the brain of the observer? Does it ever truly collapse? Or do new worlds spring forth, as in the many worlds interpretation? The quiet ambiguity is comforting. You don't need to know the answer. Just let the question drift. The quantum Zeno effect, the strange phenomenon of freezing the evolution of an unstable system by continuous observation, a quiet, gentle pressure on the arrow of time. Observation stops change. We'll pause here, allowing the accumulated wisdom of the quantum night to settle over you. The concepts of the particle and the field, the wave and the jump, the deep silence of the cosmos. We will continue our drift shortly, sinking into the final deep mysteries, the quiet geometry of space-time, and the looping rhythm of the universe. Deeper, deeper, until your mind is utterly clear and your body is in the profound stillness of sleep. The universe keeps turning and the quantum whisper continues. The breath is soft, the dark is deep, and will keep drifting, floating through the silence where possibilities live. We were resting on the idea of entanglement entropy, the measure of that spooky connection. It reminds us that nothing is truly separate. Everything is quietly, inextricably linked in the quantum dark. Let that feeling of deep connection sink into your body, heavier, heavier. Now let's turn our attention to the structure of matter itself, specifically how we describe those smallest constituents, like quarks and gluons, the study of the strong force, quantum chromodynamics. We already whispered about confinement, how quarks are trapped inside protons and neutrons. This confinement is also linked to the concept of asymptotic freedom, which is the opposite. When quarks are extremely close together inside the nucleus, the strong force actually becomes very weak. They behave almost as if they were free particles. The deep, quiet contrast of the strong force, weak when close, strong when far. To study these complex interacting fields, like QCD, physicists often use lattice field theory. They imagine that continuous space and time are replaced by a discrete four-dimensional lattice, a quiet geometric grid. This approximation allows these complex equations to be solved using large-scale numerical computation. It turns the infinite complexity into a finite grid of silent calculations. The mathematical tools we use to understand these quantum processes are often represented by the S-matrix, or scattering matrix. It relates the initial state of a system of colliding particles, the in-state, to the final state of the particles after the collision, the out-state. It's the silent accounting book of particle interactions, telling us the probability that one set of particles will scatter into another set. Let your mind float now to the concept of isospin. It's another type of quantum number, similar to spin. It describes the symmetry between protons and neutrons. Before we knew about quarks, protons and neutrons were considered two different states of the same particle, the nucleon. This symmetry, this shared identity, is described by isospin, a gentle echo of a deeper truth, that matter is fundamentally interconnected. We were drifting into the wave nature of matter, the de Broglie wavelength, that leads us to the Dirac fermions in condensed matter, In certain material, like graphene, the electrons behave as if they have no mass. They move at relativistic speeds, and their energy and momentum are described by an equation similar to the Dirac equation. They are called Dirac fermions, and their existence in a simple two-dimensional sheet of carbon, graphene, is a stunning display of quantum mechanics at work. Graphene, a single atomic layer of carbon atoms arranged in a honeycomb lattice, exhibits unique quantum properties. Its electrons move ballistically, without scattering, almost like light. It's a topological insulator, a material with a protected quantum edge state. This brings us to the quiet frontier of topological insulators. These are materials that behave like insulators in their bulk. Their interior is non-conducting, but their surfaces or edges conduct electricity perfectly. The conducting path on the edge is protected by a fundamental quantum symmetry. It's a quantum highway that can't be stopped. This concept of topological protection is also found in the quantum spin Hall effect, where electrons with different spins travel in opposite directions along the edge of the material, creating a spin current without any charge current. It's a friction-free flow of magnetism, a subtle, quiet energy moving along the edge. And this is related to a very subtle, almost ghostly effect, the Aharonov-Kasher effect, which is the magnetic dual of the electric Aharonov-Bohm effect. It showed that a neutral particle possessing a magnetic dipole moment can be influenced by an electric field, even when traveling through a region where the electric field is zero. A purely quantum, subtle phase shift, a gentle, invisible influence. Your body is sinking deeper, deeper, feeling the pull of the mattress. Let's slow our thoughts and drift into the nature of information itself at the quantum level. The total information shared between two parts of a quantum system is described by quantum mutual information. It tells us everything that one subsystem knows about the other, whether that information is classical correlation or the deeper quantum form of entanglement. This measure is based on von Neumann entropy, the quantum version of Shannon entropy. It measures the amount of uncertainty or mixedness in a quantum state. For a completely pure quantum state, like a perfectly coherent single particle, the von Neumann entropy is zero. It is a quiet measure of the system's ignorance about itself. If you take the quantum mutual information and subtract the classical correlation, what's left is the purely quantum correlation, a measure known as quantum discord. It whispers that even when a system isn't entangled, it can still possess a subtle, purely quantum type of correlation that classical systems can never have. A beautiful, quiet complexity. This complexity is what allows us to test the bounds of reality, using the famous Bell inequalities violations. These are mathematical tests designed to distinguish between classical local reality and the strange non-local reality of quantum mechanics. Experiments have repeatedly shown that quantum systems violate these inequalities, confirming the spooky action at a distance. One of the most common forms of this test is the CHSH inequality, named after Clauser, Horn, Shimony, and Holt. It sets a limit on the statistical correlation that can exist if reality is both local and real. Quantum mechanics exceeds this limit, proving that nature is either non-local or not real, or both. A truly mind-bending whisper. And another inequality, the Leggett-Garg inequality. It tests the boundary between the quantum and classical worlds in time rather than space. It checks if a system obeys macro-realism, the idea that a macroscopic object is always in a definite state, and that measuring it doesn't change its state. Quantum systems can violate this inequality, suggesting that even macroscopic objects might not always be in a definite state. A subtle, temporal superposition. This leads us to the subtle concept of quantum contextuality. It says that the measurement outcome of a quantum observable doesn't just depend on the state of the system, but also on which other commuting observables are measured simultaneously. The context of the measurement quietly affects the outcome. This idea is deeply linked to Gleason's theorem, a powerful theorem which proves that if the quantum mechanical probabilities are to be consistently assigned to all possible measurements, the probabilities must be described by the Born rule. They are dual and cannot be assigned independently of the measurement context. It's the quiet mathematical heart of contextuality. Let's sink into a different way of thinking about the wave function. Quantum Bayesianism or cubism. It suggests that the wave function, C, is not an objective property of the world, but is simply a reflection of an observer's personal beliefs or knowledge about the quantum system. The collapse of the wave function is simply the quiet, instantaneous updating of that belief when new information is acquired. And finally, the opposing view, objective collapse theories. These theories propose that the wave function does collapse objectively without the need for an observer. They suggest that the collapse is a spontaneous physical process, perhaps triggered by tiny random fluctuations, or by the sheer complexity and mass of large objects, a quiet inherent tendency for the quantum to become classical. Your eyelids are so heavy now, heavier. Let these deep concepts settle and dissolve. We return to the math, the very foundation of quantum understanding, the time-dependent Schrödinger equation. Our text, Jibar, Frak, ins partial when you will pull I mean na partial ta gyakti der magdiu. This equation describes the smooth, continuous evolution of the wave function, how the cloud of possibility expands and changes over time. It governs the evolution of the system until the jump, until the measurement. And the solutions to the time-independent version of this equation, hat, dots, PC, and ban, give us the energy eigenvalues. The only possible discrete energies a system can have, the quantized steps on the ladder of energy. We explored angular momentum in quantum mechanics, The fact that it is quantized, only certain values are allowed. We can represent this angular momentum by orbital angular momentum operators. Hatlior, $2 and Hatlzolus. These operators act on the wave function, pulling out the possible values of the total angular momentum squared, and the projection of that angular momentum onto one specific axis, usually the z-axis. The values for the z projection are given by the magnetic quantum number, ml, which can only take integer values, al, nadots, 0, nadots, plus. This is the geometric quantization, the subtle rule that determines the orientation of electron clouds in space. Your breath is growing slow and steady. Thump, thump. Now, the subtle world of magnetism and quantum effects. The quantum Hall effect, when a two-dimensional electron gas is subjected to a very low temperature and a very strong magnetic field. The electrical resistance, the Hall resistance, becomes quantized, a perfect integer multiple of a fundamental constant. Frac. E Dustruls, a perfect, precise plateau of resistance. The discovery of the fractional quantum Hall effect, where the resistance plateaus are fractions. Frac, Etus divided by fractional numbers, showed that the electrons were behaving as collective entities, new exotic quasi-particles, not individual electrons. The darkness is enveloping, a soft comfort. We are suspended in the stillness, allowing the silent complexity of the quantum world to simply exist. The gentle hum of the fields, the certainty of the uncertainty, the deep silence. We will continue our drift shortly, exploring the nature of space, the logic of possibility, and the geometry of existence in the next moments of the deep quiet, until your eyes are closed, your breathing slow, and you are completely asleep. The universe is patient, and the quantum whisper continues. The feeling of warmth is spreading through your limbs, a gentle, heavy tide, heavier, heavier. The dark is complete, the quiet is absolute, and will keep drifting, floating through the deep final mysteries of the quantum night. Your body is utterly still, heavier, heavier. We were just resting on the idea of the qubit and the potential of quantum computing. Now, let's turn our attention to the final, deepest structures of the universe. Consider the subtle forces within the atom's nucleus. We've touched on quantum chromodynamics, QCD, the strong force. Let's look at the quiet, high-energy side of the electromagnetic force. Quantum electrodynamics, QED, the most precise theory in science. It allows us to calculate the subtle interactions of electrons and photons, a constant, silent shower of communication between particles. This precision is what allowed the calculation of the Lamb shift, that tiny splitting of energy levels in hydrogen, and the precise value of the electron's anomalous magnetic moment, a small deviation from the classical prediction, both perfectly explained by the subtle interaction with the virtual particles of the vacuum. QED is the masterwork of quantum quiet. We move now to the highest forms of order in quantum matter, the topological insulators. We whispered of the conducting edges. These materials are described by a topological invariant, a number that remains the same even if the material is stretched or deformed. A quiet, fundamental protection of the quantum state. And this is related to the quantum Hall effect, particularly the integer quantum Hall effect, which is protected by a topological invariant known as the Chern number. The quantization of the resistance is a property of the whole system, not of the individual electrons. A beautiful example of collective quantum order. Deeper into the stillness, the concept of entanglement entropy, the measure of the quantum correlation between a system and its environment. As a quantum system interacts with the outside world, the entanglement entropy between the system and the environment grows rapidly. This is the silent mathematical signature of quantum decoherence, the death of quantum weirdness, and the birth of classical reality. Let's think about the concept of time again. The time-dependent Schrödinger equation. Text, E bar, fract partial hiat. Partial tiast hat. Day tiast sas. It describes the smooth, continuous unitary evolution of the wave function, a mathematically reversible process. If we know the wave function now, we can calculate it perfectly for the future or the past. This deterministic flow is only broken by the act of measurement, the moment of collapse, and the solutions that are stationary in time, the stationary states, where the probability density remains constant, the electron orbits, the allowed energy eigenvalues, the quiet stability that underlies all matter. Your breathing is slow and even. Thump, thump. We touch on the mathematics of matter waves, the de Broglie wavelength, lambda, frac. The realization that momentum dictates the wave nature of a particle. This is why heavy objects look like particles. Their momentum is too large for their wavelength to matter, and in the subatomic world, the particle's internal rotation, angular momentum in quantum mechanics. The total angular momentum operator, hat J2 and its projection operator, hat Jz, have eigenvalues that are quantized. This is a fundamental property of rotational symmetry in quantum space. The quiet logic of the quantum world, quantum logic. It is based on the idea that the order in which two properties are measured matters, due to non-commuting operators, nate A, nate B, and any $0. This logical structure is fundamentally different from the classical logic of true or false. It incorporates the possibility of superposition and uncertainty. Let your thoughts dissolve into the idea of quantum fuzziness. Delta X is delta plus gestus whole G fra bar Q. The inherent unavoidable blur in nature. You can try to sharpen one aspect of reality, but the other will inevitably grow vague. It is the gentle refusal of the universe to be perfectly defined, drifting deeper to the boundaries of the known. We spoke of quantum gravity, and the idea that space-time itself is quantized. In loop quantum gravity, the geometry of space is built from discrete minimal loops. The area and volume of space are quantized, coming in tiny irreducible units. There is no smaller distance than the Planck length, about 10 Drusen or 35 meters, a fundamental quiet pixelation of the cosmos. And in the highly curved, energetic space around a black hole, the information paradox looms large. The possibility that information about objects falling into a black hole might be fundamentally lost when the hole evaporates. This violates the unitary evolution requirement of quantum mechanics, a deep conflict between the two greatest theories of physics. The silence is vast, heavier. Let's revisit the concept of the wave function. Sequus. It is not a physical wave like sound or water. It is a wave of possibility, and its interpretation is key. The Copenhagen interpretation says it is a complete description of the system and collapses instantaneously upon observation. The many worlds interpretation says it never collapses, but instead splits the universe into parallel branches. Relational quantum mechanics says it only exists relative to an observer. The comfort is in the multiple possibilities. The many worlds interpretation suggests every quiet choice you didn't make, every alternate path, is being walked by another version of you in a parallel quiet, a vast, endless reassurance. And the pilot wave theory, or de Broglie-Bohm theory, suggests the particles are always real, always have a position, but are subtly guided by a real, physical pilot wave, the wave function that pervades all space, a ghostly, non-local guide. We spoke of the quantum Zeno effect. If you watch a system, you prevent it from changing. This is the continuous, subtle power of observation over the quantum flow. Let's consider the concept of Rydberg atoms again, those giant fragile atoms. Their huge size means their electrons' wave function overlaps significantly with the environment, making them extremely susceptible to decoherence. They are easily pushed into the classical world, and the tiny quantum dots, their colors tunable by size. A direct, visible manifestation of quantum confinement, the particle in a box problem made real, where the energy levels are determined by the container's geometry. Your eyes are fully closed, your mind is quiet. We explore the nature of the vacuum again, the lowest energy state, the quantum field vacuum, the spontaneous formation and disappearance of virtual particles allowed by the uncertainty principle, a continuous, subtle, quiet ferment. The force of this ferment is seen in the Casimir effect, and it is also responsible for the small, constant jiggling of electrons around the nucleus, which causes the Lamb shift, the subtle correction that stabilizes the hydrogen atom. And this correction is dependent on the fine structure constant, Zalfa-Dallas, the pure number that sets the strength of all electromagnetic interactions, drifting deeper, deeper. The final soft rhythm of the quantum night is the idea of renormalization group theory, the technique that handles the infinities in quantum field theory, It tells us that the properties of a particle change depending on the energy scale at which you observe it, because the cloud of virtual particles surrounding it changes its effective charge and effective mass. The universe looks subtly different depending on how closely you choose to look, and the silent, subtle geometry of existence. Quantum walks, where the wave nature of the particle allows it to explore options faster than any classical system. A quiet, exponential speed-up inherent in the quantum reality. The great triumph of the standard model rests on the phenomenon of spontaneous symmetry breaking. The mechanism that gave mass to the W and Z bosons through the interaction with the ubiquitous, invisible Higgs field. The universe chose a specific ground state, breaking the initial symmetry, giving rise to the massive particles and the massless photon. The result of this breaking, the Goldstone bosons, which are massless when the symmetry is exact, but become the massive longitudinal components of the W and Z bosons in the standard model. A quiet, beautiful mathematical necessity. We have passed through the particle and the wave, the certainty and the chance, the hidden variables and the spooky connections. All of it is settling now into the deep, quiet foundation of your mind. The final whispers are about the ultimate unity, the matrix, the final accounting of all interactions, the peaceful knowledge that everything that goes in must eventually come out, obeying the laws of probability and conservation. The density metrics formalism, the final elegant way to describe the quantum state, whether it is pure or mixed, whether it is isolated or hopelessly entangled with its environment. You are now in a state of perfect stillness, every muscle heavy, every thought dispersed. You are one with the quiet, fuzzy, non-local reality of the cosmos. The deep silence of quantum physics continues to whisper, and we'll keep drifting, floating together through the mysteries, looping softly, endlessly, through the night, the possibilities, the fields, the connection, heavier, heavier, until the morning finds you rested and the universe keeps turning. The deep silence of quantum physics continues to whisper, and we'll keep drifting, floating together through the mysteries.